So to continue, we're talking about the estimation of hourly radiation based on the daily radiation that we have. So the ratio that we are looking for is RT, ratio of total radiation. By total here, I mean the components, beam as well as diffuse radiation. So RT as a function of I over H is being provided, and the designated hours are given by the time corresponding to the midpoint of the hour, which means that we're around solar noon, and plus or minus the values are being designated through a figure or through a correlation. This is the figure where we can get this value, the RT, or the ratio between I, hourly radiation, and H, daily radiation, is being given here as a function of, look at the two x-axes that we have. You'll find we have that hours from the sunrise to sunset, which is capital N, the day length. And the day length here is basically calculated as either from a figure or from a chart, a table. So we have a figure and a table that provide us with the value of capital N. And the sunset hour angle, omega S, we have a correlation that provides us with the value of omega S. Now the 0, half, 1.5, 2.5 are basically the middle of the hour in which we are looking for this change. For example, we are looking at a change at a certain hour, we get in the middle of the hour, and that will be far from the solar noon by either half, 1.5, and that's even the plus or minus are going to be treated similarly on this figure. And the correlation that we can use for RT can be seen here as equation 213-2A, where A and B are again functions of omega S given by equations B and C. So to obtain the value of RT, which is the ratio between the hourly and the daily radiation, we have one of two options: either to use this figure to obtain this value, and the input values are the same, or to use the correlations. And for the correlations, definitely we'll need to go ahead with a little bit of additional values to calculate, which are, for example, related to the sunset hour and the hour angle, as you can see here, omega and omega S. We have an example here to do this. So to ask about the fraction of the average daily radiation received in a city in Australia, Melbourne, at the hour between 8 and 9 in the morning. For Melbourne, the latitude angle is 38. And then the mean day of January is 17th. This is obtained from table 161 in chapter 1. And the equation that we have seen earlier, 161, that's the equation I'm writing here next to it, which is calculating the declination angle, which is given as the day of the year. And then finally, equation 1611 that calculates the value of capital N. And again, capital N is the duration of the sunrise from sunrise to sunset during the day. And on that day, the day length is 14.3 hours. Then we go to the figure, knowing the value of delta and knowing the value of N. We are talking about 8 to 9 a.m. So we're going to estimate it at 8:30, and 8:30 is 3.5 hours from the solar noon. Then for a day length of 14.3, the figure 12.3a would provide us with a value of RT, which is equal to 0.078, or 7.8% of the daily radiation will be in that specific hour. So this is basically the figure that we're looking for. We have calculated the value of the day duration, or the length of the day, which is capital N. Then we are going to move vertically up until it hits the 3.5 figure here, and then moving to the left, you can estimate the value as it has been obtained here as 0.078. So this is how you can use the figure for obtaining this value. Alternatively, we could have used the correlation here, but for the correlation, we have to go one extra step by calculating the hour angle, omega and the sunset angle omega s. And once we know omega s, you can estimate A and B, and then you can substitute these values here to obtain the value of RT. Doing that, it has provided a value of RT, which is 0.076. Of course, the omega s, we are going to get the correlation for omega s and the equation that we use to calculate omega. Then we're going to substitute into the equation and we'll get a value which is, I mean, it's a very close value. The difference is only 0.002. So using figure or using a correlation, it will be optional to you unless you're in a situation where either one of you is provided. One of these are provided. Now we have calculated the ratio. What about the value itself? Another example has been given here. The total radiation of Madison on August 23 is 31.4. Estimate the radiation received between 1 and 2 p.m. So we're talking about here, the hour is 1.5. We're looking at 1:30 p.m., which is different from the solar noon by 1.5 hours. So for Madison, the value of delta has been calculated earlier in examples as 11 on 23rd of August. And for the 23rd of August, which day of the year is it? You can either calculate it, as I mentioned earlier, by going month by month or just jumping to table 161. That will give you, for calculations of August, then the 23rd should be added to a value of, I have that table in front of me. So for August, it should be like 212 plus I, and I is 23. So you can get the value of small n, or the number of the day in the year. Then you substitute that in the correlation that provides us with the declination angle. You calculate delta. We know that phi is equal to 43 for Madison. Then going to figure 163, you'll find that the sunset is at, which is the figure given by Wheeler, or if you like, you can go to the correlation or the equation that provides us with omega s, which is the sunset hour. And the day length, again, capital N, there is a couple of options for it. Either you may obtain it from a correlation or from a figure. So we can get the value of omega s, we can get the value of capital N, and then from the figure, knowing the capital N, and for a mean hour of 1.5 from solar noon, you can get the value of RT as 0.118, or you may, if you like, obtain it from the correlation. Then this is 118 is the ratio between I over H. H is 31.4 as given in the example at the top of that slide. So 0.118 multiplied by 31.4, it will get a value of 3.7. And here is some sort of a note that this value can be measured by the instruments and the value will become as 3.47. So that gives like the margin of error in the estimation of this value compared to the measured values using instruments. And that basically is due to the use of the correlations, which have some sort of approximation that results in some certain level of error, which is acceptable in these cases. I'm seeing here that Yasser Shaithir is trying to join for a bit of time, so I'm not sure whether he could join us or not. For me, it appears that he is joining. So Yasser, if you have not joined so far, you may think of what I did by rebooting your computer, putting it off and on again, and then you'd be able to join us.
No, I joined, doctor.
Oh, so okay, fine, because
Yeah.
it's showing me as you are joining. So it seems that there's some issue here with.
No.
Fine, okay, then I'm glad you're here. That's the problem with the technology, that everything is fine, but whenever you have a problem, then it's a disconnection issue. Now, what we did so far was looking at the RT, and the T here stands, or the subscript T in what we have done earlier which is like this. It is referring us to the total radiation. What if we need the components? Looking at, for example, diffuse component or beam component of the radiation. For such a case, this has also been considered, and you can see a figure here, and the y-axis of the figure is basically R sub D, which is ID over HD. D here stands for the diffuse component of the radiation. So the ratio between the hourly diffuse radiation to the daily diffuse radiation, diffuse component of the radiation, is being given here in this figure and also given by equation 213a. So it's not only that we can calculate how much is the total radiation in an hour based on the daily radiation, but we can even get the component of the diffuse radiation of this hour. And that is basically what we are doing here in this figure. This is the value that I'm referring to, which is ID over HD. And the equation here, as the definition of ID over HD, is given here by this. You'll find this equation is very much similar to the previous one, except for an expression of 1 minus cosine omega s. So both of them are basically somehow similar to each other, or there is a similarity except for one component. And there is an assumption here, and this is the case when you are trying to convert measured data into either figures or correlations, that you have to come up with some assumptions just to simplify the calculations. So we are considering the ID over HD is the same as the I over HO. What I over HO? It is basically the kind of same ratio, which is the hourly to the daily radiation, but the O here stands for extraterrestrial radiation. So we're talking about the components outside of the atmosphere. So assuming that the ratio outside the atmosphere is the same as the ratio as it comes closer to the ground. And that's the assumption based on which this expression has been developed. Let's have an example here. Talking about the average daily June total radiation on a horizontal plane for Wisconsin, Madison is 23 megajoule per meter square. Estimate the average diffuse, the average beam, and the average total radiation for the hours between 10 to 11 and between 1 to 2. So we're talking about like 10:30, so the which is 1.5 hours deviated from the solar noon. And we are going to follow the same procedure that we have done earlier. For example, for the value of H naught for Madison, and the value of H naught, as you might have remembered, it's either obtained from a correlation or from a figure. And there's a correlation that gives us the value of H naught here, and it's been used to calculate the value of H naught for Madison as 41, roughly 41 megajoule per meter square. And this is obtained again either from table 110.1 or from equation 110.3 with n equal to 162. N here is the middle day of June, and according to table 161, the middle day of June is being specified as 11th of June. So 11th of June has been considered. And for 11th of June, small n is equal to 162. The small n, again, I would remind you that starts with 1 at January 1st, and it ends with 365 at December 31. So the value of H naught, we have two sources to calculate it, either from a table or from an equation. The value of n, you can either calculate it or you can refer to the table to obtain it. Omega s, I've added the equation down there for calculating the sunset angle. And the daily length, which is again capital N, and capital N can be obtained either from a figure or from equation 1611. Knowing all these values, then we can do like what we did in example 2.12.1 by calculating KT. KT is H over H naught. H naught has been calculated, H is given, so we can get the value of the KT here, and from which we can calculate the ratio HD over H is equal to 0.38. The HD over H, again, it's been given. As we did in example 12.1, let me get the example quickly to you so that you can remember how this value has been obtained. Yes, here is it. So we're talking about again Wisconsin-Madison using the equation of H node. This is the one I mentioned. You can use this equation to calculate the value of H node, and the value of H has been obtained from the appendix, from the data, to be as 23.0. So dividing 23.0 over 41.8, which is the H node calculated from this equation, you can get the value of KT. Now we have known the value of KT as equal to 0.55 accordingly. Back again to our example. So the KT, which is H bar over H naught, is 0.55. The HD can be obtained as 0.3A, and the average daily diffuse radiation is this ratio multiplied by the 23, which is capital H or H bar, then the value is 8.7. Oh, there's an issue here. Sorry, it seems I have an issue here with my computer today. So it's 8.74 megajoule per meter square. Going to the figure, which is 213.2, now we have known the daily diffuse radiation. We need the hourly diffuse radiation between 10 and 11. So we're going to go to the figure 213.2 and try to obtain the value of RD. What are the information that we have? We have the daily length, capital N, as 15.1, which is either obtained from the Wheeler equation or obtained from the correlation of capital N. We have seen it in one of the previous slides. And 10:30 in the morning, which is 1.5 hours away from 12. So that's a value of 1.5. So we have the 15.1, and we have a value of 1.5 here, which is this one. Then we can get the value of the ratio ID over HD, which is 0.102. Actually, if I'm going to go to this figure myself with this value, I could have just obtained a value of 0.1. So being able to obtain 0.102, which means that I would use the correlation to do that. But I mean, by my eyes from the figure, I could roughly get it as only 2 digits, 0.1, which is, again, it's not too far. Or you can use the equation, which is equation 213.4, and calculate the value of RD. So that's the other option. And as usual, the other option will require us to calculate the hour angle and the sunset angle. Once you do that, you substitute here and you get the value of RD. And if we obtain this as 0.1 and this one as 0.102, then they are close enough from each other. Then the average component of the daily diffuse radiation we obtained was 8.74. This is the fraction of this hour of this radiation at that hour. So the diffuse component here is the 0.102 we obtained from the graph or the equation multiplied by the value of HD, and accordingly it becomes as 0.89. So this is the average diffuse radiation between 10 and 11 in the morning. Same thing can be repeated for the afternoon, and you are going to get a value between 1 and 2. This is the diffuse component. And you already know the total component. The difference between them is going to be the beam component. And that's why it is given here at the last line here. The average beam radiation is the difference between the total radiation that we calculate, the diffuse radiation that we have just calculated at the last step. And you can see here for this case, for example, from the curve for 1.5 hours from solar noon, and for a daily average length of 15.1 hours, this is capital N, for RT equal to 0.108, which is the case here for the 1 to 2 in the afternoon, which is basically 1:30, 1.5 hours from the solar noon, you can get an RT1 0.108, and an averagely hourly total radiation of 0.108 of the daily radiation, which is 23, so the value is 2.48. Now, this is the total. And we have calculated the diffuse component to be 0.89. The difference between them is the beam component. So again, we are able to calculate the total radiation at this hour, and we are also able to calculate the components of it, the diffuse radiation and the beam radiation. We calculate the total radiation, the diffuse radiation, and the difference between them is going to be the beam radiation. The surfaces that we are using are not horizontal. And we have seen that before. We are doing like tilting of the solar collectors by a tilt angle. If you remember, the symbol was beta, so that it receives more radiation over the day. So how to be calculating the radiation on sloped surfaces, which are having a certain tilt angle, this is what we need to look at as a next step. So we're looking at a general problem to calculate the radiation on a tilted surface when only the horizontal radiation is known. If you remember, before we said that what the kind of data that you can find abundant is the radiation on a horizontal surface. And then what we need to do is to convert this amount of radiation on horizontal surface to a radiation of a tilted surface. Have we done that before? Yes. The answer is yes, we did it, but we did it for the beam component only. So section 1.8, which is basically one part of the section in chapter 1, we used to get this or to calculate this component, RB, which is the irradiation or irradiance falling, the tilted on the horizontal surface. But what we did calculate was basically the component of the beam radiation. We did not do it for the total radiation or including the diffuse part of it. So this is basically what we need to look at now, being able to calculate the fractions of the radiations that are diffuse and how much of it is a beam radiation. Then we are in a position to look at estimating the total or the diffuse radiation which is falling on a sloped surface. It has some processes and some components associated with it that we have not been introduced to before. Like what kind of components of diffuse radiation that is going to contribute to our calculations of this ratio. It's not only a matter of a component of diffuse radiation which is falling from the sky or from the sun to the earth, because there are other components. When you are putting a solar collector with a certain slope, the definition that we talked about earlier for solar radiation is that any surface at a temperature greater than 0 starts to emit radiation. What is it that we are interested in is the net exchange of radiation between surfaces. When you are putting a certain solar collector at a certain tilt angle, it is receiving total radiation, beam radiation, which is directly coming from the sun through a beam, and diffuse radiation, which is coming not only from the sun, but from all the surroundings. Which means that a solar collector or a tilted surface in general, let it be a window, it is receiving radiation from all surrounding objects. Not only that, but it is receiving radiation which is being reflected from the ground. So these components are what we need to consider to be able to calculate the total diffuse radiation in addition to the beam radiation which is falling onto the surface. And these components are being shown here. There is what we call the isotropic part, which is received uniformly from the entire sky dome. So from all the sky dome here, assuming that there is a hemisphere which is above this object, from this hemisphere there is radiation, diffuse radiation, which is isotropic. Isotropic means that it does not depend on change in the angle. It is just coming uniformly to the surface. The second one is the circumsolar diffuse. It's a diffuse radiation which is coming from the same source as the beam radiation. It's some sort of coming through an area which is basically originated from the sun and falling into that object here. The third one is what we call the horizontal brightening, and which is concentrated near the horizon. That's something which is coming from the horizon here, from some sort of horizontal plane. These are three components that are contributing to the radiation on a sloped surface. And remember, the definition of beam radiation is only considering a beam radiation falling from the sun, and it has not been scattered or reflected. It's just went directly from the sun to the object or to the surface, which is we are considering. Whereas the diffuse value, this is some sort of, the word diffuse itself, it means that it is spreaded. So this is coming from all around the surface. So that has the three components: the sky dome, which is this, the circumsolar diffuse, which is this, plus the horizontal component. And these components are being given here. So the I, the total radiation at a certain hour, is the total beam radiation, then the isotropic radiation from the sky dome, and then we are talking about the second component, which is basically what we are calling the circumsolar diffusion, which is the CS, circumsolar, and then the HZ stands for the horizontal radiation, and then finally the reflected radiation from the ground. The reflected radiation from the ground, it becomes essential for places where, or especially for places where there can be some sort of snow which is covering the earth. Snow is white and it has a high reflection. This is definitely, it would be a different in areas which is covered by sand. It's different in areas which is covered by asphalt, which is basically black in nature. So that depends on the kind of coverage that you have on the ground or the surface that you have. So the subscripts CS, ISO, which is isotropic, it is independent of the direction. CS, which is circumsolar, the circle of the solar energy, which is the diffuse component, is falling onto the surface. HZ stands for horizontal, and REFL stands for reflected energy, which is coming from the ground. So for yes, go ahead.
Can you repeat the second one? I did not understand.
Let's talk about the components again. Here we have a tilted surface, and this tilted surface is receiving components of the diffuse radiation, which are basically divided into three. It is receiving radiation, which is from all the surroundings, from the sky dome or the hemisphere on top of it. So there's exchange of radiation between the hemisphere, the sky hemisphere, and the surface. That's number one. Number two is the circumsolar radiation, which is the same direction of the beam radiation coming from the sun. The sun is not a point. Actually, it's a whole surface. And accordingly, moving from the origin and going in a conical shape, that is what is defining what we call the circumsolar diffuse radiation. So it's not a value of a beam, a certain point in the sun, but it is basically as if you are considering the whole disk of the sun is, and basically the halo which is around it is providing us with not only a single beam, but it's an area, a distributed area for even radiation which is falling in. The third component is the horizontal component, which is taking care of all the objects that are around it. The objects are basically at low temperature compared to the sun, so it's a long wavelength radiation sort of. Is it clear?
Yes. Thank you.
You're welcome. So the total incident radiation is basically given in terms of all of these components together to be calculated. So one of them is a beam radiation. All the rest are diffuse radiation, one of them or one component of them is reflected radiation or reflected long wavelength radiation from the ground. So on a sloped surface, these are the components that we have. AC, this is the surface area. This is the total hourly radiation falling. And here we have IB is basically the beam component of it. And then we are talking about the isotropic component. And look at this. Now, when you are talking about a surface which is receiving radiation or exchanging radiation with another surface, the other surface could be the sky circumference, or it could be only the disk in which we are calculating the circumsolar diffuse radiation, or the ground. Whenever there is radiation exchange between two surfaces, then we are looking at the fraction of the energy leaving one surface, reaching the other one, which is nothing but the definition of the radiation shape factor. And that's why the radiation shape factor is coming here. So this is ISO. So we're talking about the sky. So the area of the surrounding sky into the shape factor from the sky to the surface, the area of the circumsolar disk, which is area of basically the surface that we have, exchanging of radiation with the horizontal, so area of the horizontal surroundings into the shape factor between the horizontal surroundings and the surface. And finally, when we are talking about objects which are reflecting, the reflection is not only from the ground, but it's from any other surfaces which is around. So the surface is surrounded by walls from other buildings, by trees, by whatever object in addition to the ground. They are all receiving and reflecting energy which is falling on the surface. That's an issue here because having to calculate all of these areas, sometimes these areas are not easy to calculate. And because of that, we are going to get back again to what we studied in heat transfer as the radiation shape factor correlations or properties of the shape factor that can make our life a bit easier here. Let's look at this again. The first term in the equation, this one represents the beam radiation. The second one is the isotropic diffuse radiation, which is basically coming from the sky to the collector. And that's why area of the sky is being given here, and the shape factor from the sky to the collector. The third component is the circumsolar diffuse radiation. It is treated as if it's coming from the sun right away. And then the horizontal component, which is the fourth component here of the hourly radiation. And you see here, it's coming from the horizontal, the surfaces around it, and that's why the surfaces areas are being accounted for here. And this is sigma. Why sigma? Because when you are talking about the ground sort of radiation, we're talking about the earth, the buildings, trees, whatever is surrounding the unit. And for each one of them, it is accounted this way. So for each one of them, we should calculate the value of I, the reflectivity, the area of that object, and the shape factor between the object and our surface, which is too much to do. I mean, when you are talking about a solar collector, it's not placed in a room. It's placed in outside, and it is definitely, or normally it would be surrounded by other surfaces, like, as I mentioned, like buildings, adjacent buildings, or trees, or any objects that are around us. And that becomes tedious to account for. And this is why the radiation shape factor properties are going to be useful here, which is basically some sort of properties of what we have learned in heat transfer course that are going to make our life easier. However, there is some sort of an approximation that can be done here, that this component here, it doesn't make sense to look at all the surfaces which are around us, but maybe it's a good idea to assume all of these as a one component, which is basically what we are going to consider. So we are going to combine all of these in one component, and this component is the one that we are going to consider. As if all the surrounding surfaces are represented by one surface, let it be the ground. So it's only the ground that we have to worry about the reflection from. So the ground here is an approximation to every other object which is surrounding our sloped surface. A reminder, this information here is something that you have covered previously in heat transfer course, in the radiation part. To remind you, the view factor or the shape factor relations will have the reciprocity, that if we have two surfaces and the two surfaces are at two different temperatures, then the way that they are exchanging radiation with each other. For example, let's look at the figure that we have here and consider surface T1 and surface T2. This surface has a temperature T1, this surface has a uniform temperature T2. Then the exchange of radiation between them is occurring. There is radiation leaving surface T1 reaching for T2, and there is radiation leaving T2 going to T1. The shape factor says how much is the exposure of one of these surfaces to the other, which means that how much of the energy, fraction of the energy leaving surface 1 is falling on surface 2. It depends on how big the surface is, how close they are, and how the orientation between them is done. The reciprocity relation is saying that A1 F12 is equal to A2 F21. This is going to make it a lot easier for us when we think of it as we get back to this. For example, I don't know how much is the horizon area or the horizontal surface area. So I can replace this simply, and instead of A horizontal, F horizontal to C, it can be AC, area of the collector, into FC to the horizontal. FC to the horizontal is easier to calculate. And the same thing applies for this. F from sky dome to the surface, and the shape factor from sky dome to the surface. I can replace it by area of the surface, shape factor from the surface to the sky dome, and there are correlations or figures that give that shape factors. The same thing here when we are talking about a horizontal surface. And instead of saying AI FIC, it will be AC FCI. AC is the area of our collector, which is known to us. FCI is the shape factor from this collector to the surrounding, which again is easier to calculate. So we're going to convert this equation into a simple equation that we can use for our calculations in an easier manner. The other radiation property is what we call the summation rule, which means that the radiation, the shape factor, F12 plus F13 plus F14 plus F15 plus F16 plus F17 is equal to 1. What is the shape factor? It's a fraction. So simply, whatever is leaving surface number 1, part of it will fall into 2, part will fall to 3, part will fall to I, part will fall to 5, part will fall to 6, part will fall to N. The total, these are all fractions that are going to sum up to the total radiation leaving surface 1, which is a value of 1 as a ratio. So the summation of radiation leaving one surface and going to all the surrounding surfaces is equal to 1. And normally we can make use of this kind of correlation if you remember the problems that we had in shape factor for heat transfer. For example, if I have a component, sorry, for example, surface 1, surface 2, surface 3. We have correlations that give me shape factor between 1 to 2. So if 1 to 2 is known, if 1, 2 is known, then I can use this equation as f from 1 to 2 plus f from 1, 3 is equal to 1. If I know this one, then I can determine this one. And this apply not only for a 3 surface system, but for n surface system as the one that we can see here. So this is the second property of the shape factor. And there's another example of the shape factor that sometimes you do not need correlations. For example, if you have concentric cylinders that are infinitely long or concentric spheres, all the radiation leaving surface 1, definitely it should fall on surface number 2, because surface number 2 is containing surface number 1. Accordingly, the radiation F from 1 to 2 is equal to 1 because all the radiation leaving 1 is going into 2. But it is not vice versa because radiation leaving surface 2 can still fall on surface 2, especially if surface 2 is at a non-uniform temperature. Accordingly, only a fraction of 2 is going to fall into 1. So the radiation properties are useful here. If I need the value of F2 to 1, then I would simply say that A1 F12 is equal to A2 F21. A1, surface area of 1, say it's a long cylinder, so pi dl. F12 is equal to 1. A2 is pi d outer L, so I can calculate F2 to 1. So this is an example of utilizing the reciprocity in calculating the shape factor in one of the cases. Suppose that it's not easy like that. It's not a simple case in which we have a concentric cylinders or spheres, but it is rather something which is doing like this. Then we have surface number 1 and this is surface number 2. Then we have the shape factor figures and shape factor correlations that are being used so that we can calculate the radiation shape factor between two surfaces. Suppose that this is the case, and I already could be able to calculate F12 from a figure or a correlation. Then I can use the reciprocity to calculate F21, so that A1 F12 is A2 F221. We might be able, maybe next week, we are going to have some sort of a quick revision to some topics of the heat transfer course that are relevant to our course. Maybe we can touch base on the radiation shape factors again. And I would just recommend it so much just to pay a visit to the heat transfer book and look at these shape factor correlations and the equations and figures that are used to determine the shape factor, including something that we call the cross-string method, which is a method that we can do sort of algebraic expression to calculate the shape factor between two-dimensional surfaces. Why did we go into this? Because we wanted to set this issue of the reciprocity relation, as you can see it here. So what I just mentioned a while ago is that we will try to make it easy for our calculations by using the law of reciprocity for the radiation shape factor to replace all these areas that we cannot determine: A sky, area of the horizontal surfaces, area of the ground, which is a representation of this expression. We are going to replace all of that by the radiation shape factor relations, which are again repeated here, so that the calculation becomes a little bit simpler. And I brought that here in this slide so that you can see this kind of change. We are moving from equation 214.2, talk about radiation for sloped surfaces, from the original expression that we have written into an expression which is simplified by using that radiation shape factor expressions, as you can see it here. So what we did here is a couple of things going from equation 2 to equation 3. Number one, we are considering the reciprocity. So basically, AS sky, F sky to the collector is going to be replaced by A collector, F collector to sky. A horizontal, F horizontal surfaces to collector is going to be replaced by A collector, F collector to the horizontal surface. And we said that this component or the sigma here is going to be replaced by I, rho ground, reflectivity of the ground, area of the ground, shape factor from the ground to the collector. So we're going to use the reciprocity here to represent this as definitely I and rho g remain as is, but we are going to replace this with A, C, F, C, and G. When you see that, you'll find that almost every term in the equation has the expression of AC. So we're going to divide by AC as well. So IT is going to equal IB, RB, and this value, we know how to calculate it from the correlations we had earlier. I, diffuse component of isotropic value, shape factor between the collector to the sky, ID circumsolar, RB, again RB is here, and then the horizontal surface, F from the collector to the horizontal surface, and then F from the collector to the ground. Now this equation 214.3 is much easier to handle compared to the previous one, because this is all has been written for the collector surface area to the extent that we divided by the surface area. It was common everywhere here. And it's only these kind of shape factors that we need to determine, which are easy to determine or easy to get from shape factor figures, equations, as well as the properties of the shape factor. So that this is the equation that we have reached for 214.3, which is, I'm showing it here, but here I'm showing exactly how did we reach this equation starting from that, using the law of reciprocity and the approximation of the ground here for the last term. So the equation is given here. Then we're talking about here the total radiation falling on a tilted surface, which is IT, divided by the total radiation on a horizontal surface, which is I. At the end, this is what we want. We have a total radiation falling on a horizontal surface, but our surfaces as collector is tilted, so we need to get that component of the tilted radiation over or in comparison with the horizontal surface. Why again? Because most of the data that are available for solar radiation are available for horizontal surfaces. And we need to modify it to values of radiation falling on a tilted surface. Now, it's not only that we have covered so far, but there are even simplified sort of correlations that came into the picture. Part of the correlation is assuming the isotropic diffuse model, which means that it says that we are going to deal with only the components of beam, isotropic diffuse, and solar radiation, which is reflected from the ground, are going to be considered. The other components are going to be neglected, assuming that everything is diffuse. Diffuse means what? It means that the radiation which is coming from the dome of the sky is representing all the kind of falling radiation into the surface. But talking about the issue of the circumsolar disk alone or the horizontal components, this contribution is basically has been considered in the isotropic condition. Isotropic again means it is independent of the direction. Because it's independent in the direction of the direction, so there's no point of considering different components of it or further components. Accordingly, term number 3 and term number 4 from the equation are going to be neglected, and we are only going to consider terms 1, 2, and 5. So this is what's called the isotropic sky model or isotropic diffuse approximation of the equation. Why are we doing that? Because again, we are looking for a simpler way to represent that IT or the total radiation falling. Remember again that before getting too much with the computer use, calculations were done by hand, and people wanted some sort of a quick way to calculate it, either from a simplified equation or using a figure. Approximations are going to be fine as long as the accuracy is kept, which means that if you are going to get a value with an easier calculation, which is within a certain deviation from the accurate value, still you can accept that. We as engineers are basically using safety factors. If you remember in machine design, you probably have calculated the thickness of the wire rope that carries the elevator. And you found the thickness is a certain value, D. What you do? You multiply it by 10 as a factor of safety. So that's something similar to that. We are talking about a value which does not have to be exactly the same number, but it's a range. Accordingly, if you are going to simplify your equation and having that the accuracy is not going to be affected drastically, then still you can live with that. So going to the shape factors, a surface which is tilted at a slope beta from the horizontal has a view factor to the sky. This is obtained from the view factor correlations you had in heat transfer. That's equal to 1 plus cosine beta over 2. So a shape factor here is easy to determine. If diffuse radiation is isotropic, this is also RD. So that also remains or represents RD, which is the ratio of diffuse on a tilted surface or to the diffuse of the horizontal surface. Now, taking that shape factor into considerations again, and the shape factor from the surroundings to the ground has been calculated from the shape factor correlations to be 1 minus cosine beta over 2. So taking the two values of the shape factors that we have determined here, we have shape factor from the surface to the sky, shape factor from the surface to the ground. The one from the surface to the sky has been obtained from shape factor correlations to be 1 plus cosine beta over 2. Beta is the tilt angle, and the one from the tilted surface to the ground has been calculated as 1 minus cosine beta over 2. We are going to substitute these values here in this equation and come up with this equation, which is basically IB, RB. This is the beam component, ID, diffuse component, 1 plus cosine beta over 2. So this is the only representation of the diffuse component because we're talking about what we call the isotropic model. And for the isotropic model, it is independent of the direction. So just one component of the diffuse radiation is considered, ID, and the shape factor is considered. And finally, the reflected energy from the surrounding with the shape factor accounted for here. Now, by the definition, what we are looking for? We are looking for not only for the value of IT, but we are looking for the ratio IT over I, which is capital R. So capital R here, or the ratio, is given as, we are dividing every one of these components by I. So IB over I into RB, ID over I into the shape factor. I will cancel with the I, so it will be rho G into 1 minus cosine beta over 2. So this is the solar radiation on a tilted surface for an hourly case. Let's have an example here. And I think that we are going to take this example as the last component for our class today. So using the isotropic diffuse model. By the way, the isotropic diffuse model is not the only model which is there, but there is a couple of other models that have been considered. The one that we have here is the simplest one. It has just come here and said that let's cancel term number 3 and term number 4 of the equation, assuming that we have isotropic condition, and this is it. And that's a simplification to the model that we have. But others came with further assumptions which are a little less simple compared to this one, but a little bit more accurate. So using the isotropic diffuse model, estimate the beam, the diffuse, and the ground reflected components. Here we are looking at the 3 components that we are considering of solar radiation and the total radiation as well on a surface with a slope of 60 degrees. So beta is equal to 60 here toward the south at a latitude of 40 degrees north. So this is phi for the hour 9 to 10. So here we are considering 9.5 or 9:30, which is 2.5 hours. On February 20, so the n, small n here is 31 of January plus 20, this is 51, small n is 51. Here I is equal to 1.04 megajoule per meter square, and the ground reflectivity, rho G, is 0.6. Now for this hour, the value of I naught is given as 2.31 megajoule per meter square. The value of KT is the ratio of the 1.04, the I which is given here, divided by I naught. So KT is given as 0.45. And then from the correlation of figure 210.1, I repeated this correlation here as a reminder. The value of ID, it depends on the value of KT. KT here is 0.45. So the equation in the middle is the equation that we are going to consider to calculate the diffuse component over the total hourly radiation falling, and this value has been calculated when you substitute KT is equal to 0.45 into this equation, you get a value of ID over I is equal to 0.757. Accordingly, the value of ID is going to be calculated. The 0.757 is the diffuse fraction of that hourly radiation falling. So the beam fraction is going to be the total radiation minus the diffuse radiation. So the radiation is 1.04. The diffuse component is 0.757 of this, which is basically calculated here at 0.787 megajoule per meter square. The beam radiation, it can be either the 1.04 minus 0.787 or the 1 minus the fraction 0.757 multiplied by the 104. You get this value here. So now we could get the hourly diffuse and beam components of this radiation. Now the hour angle, omega, we're talking about 9:30 in the morning. So we substitute for omega, which is 15 into the hour, the solar hour or solar time minus 12. You can get a value of minus 37.5. Delta, declination angle, which is a function of n, which is the number of the day in the year, has been calculated as minus 16.4. You take these values and substitute it in the RB connection. RB is the fraction of the beam radiation, and we have covered that at the end of chapter 1. And this can be calculated here, so 1.71 of the horizontal radiation. This is how the beam radiation has been expected or calculated here on that surface of beta equal to 60. So RB has been calculated here, and then the value of IT, the correlation that we have taken, the three components which are basically given by that expression here. What we are calculating IT, and the I sub T is basically IB, RB. We have calculated RB already. IB is given to us. We have calculated in the previous step. ID, and then cosine beta, beta is equal to 60 degrees, and rho g, the reflectivity is 0.6. So substituting directly into this equation, here are the components, and it can be calculated as 1.18. Now the three components that we have, this is the beam component, which is a fraction of 0.33. This is the isotropic expression, which is 0.787 into 1 plus cosine beta over 2. The value is 0.59. And finally, this is the reflected radiation coming from the ground. So the three components have been added together to give this total. The beam contribution is 0.43. The diffuse component is 0.59. And finally, the ground reflected is 0.156. The total radiation of the surface is 1.18, the one that has been calculated here according to this equation. Definitely, because there are correlations with certain assumptions, there's some sort of uncertainties that are associated with this calculation. And the example that we have taken here has been done assuming that it is facing south. So the azimuth angle is 0. This model is, however, applicable to any orientation based on you are able to calculate the value of RB correctly. That takes care of this part, or basically we're looking at the diffuse component of the radiation simplified by the isotropic model. But as I mentioned, the isotropic model is not the only one which is available. There is a couple of models that do exist other than this one. And these models, just to give you a quick idea about the difference in assumptions, the models are basically, it can be shown here. Yes. This is another model which is called the anisotropic sky. It's not isotropic, it's anisotropic or anisotropic model. And getting back again to the basic equation that has the beam component, the isotropic component, circumsolar component, horizontal component, and reflection component. And then the HDKR model, which is the second one here, is based on the assumption that all diffuse components can be represented by two parameters. So the diffuse component, like IDT, for example, is represented by these two parameters here. Whereas there's a third model that's called the Perez model, has seen no, that we can represent it by three equations or three terms, not two terms. So the three terms are, this is the first term, second term, and third term. All of these are some sort of putting more details in the calculations with the target of reaching for a more accurate estimation. Definitely, when you are getting from the isotropic model to the HDKR model to the Perez model, we are going a little bit more complicated, but the results are more accurate as you are getting more and more involved in the calculations. Which one of these models to be used? The isotropic is the simplest. It gives the most conservative estimate of the radiation on a tilted surface. The HDKR is as simple as the isotropic model. It just had one component additional to it. It gives results that are closer to the measurement values, so closer to the true values. And it can be used if you are if you are having surfaces that are sloped toward the equator. The Perez model is more complex. It predicts value at slightly higher than the measured values, but it's the least conservative. It's the more accurate of the three models. It agrees well or better with the experiments, and it is recommended for cases where gamma is far from zero, which means that it is not facing south, but it is tilted away from the south, and this is where the value of the Perez model can be suggested. For people dealing with currently with this kind of estimations, if you are going to write your model in an equation and the equation is going to be stored in the computer, then there's no problem going to the more complex one. It's not very much complex. It just have a little bit more components into it. If you are going to identify the input values and put it all there, then it's not a problem. It's not like that somebody is going to do every calculations by hand. Accordingly, that's something that you may keep in mind when you are considering these three different models: the isotropic model, the HDKR model, and the Perez model. All of them are representing the values of the tilted radiation, and the way that they are different only in the evaluation of the diffuse component of the radiation. I'm going to stop here, and then we'll continue next time. Next time I have a couple of things to do. We're going to continue this chapter or complete this chapter on the class of Wednesday, inshallah. And then we are going to have our first quiz. The quiz is going to be on chapter 1, which is something very much related to the homework that you have taken. To get a little bit more of engagement from now on, I think whenever we come to a solution of an example, starting from, I'm not sure the time will allow us because of the quiz on our next class or not, but later on, at least on every class, one of the examples is going to be done by some sort of a group solution. So it will be some sort of a common work, so that I would guarantee that you are alert with me, that you are contributing. Maybe even we can do it as groups. So we'll have like the equations of the model, which basically needs some sort of simple calculations. And you are going to be forming groups. Maybe I can form the group from my side, so that whenever you have an example, you just get your hands on. So be prepared with a calculator with you, and then we can do that sort of exercise. So it will just get your hands running as we are going from class to class, inshallah. You have any questions?
Yes, Doctor. During the quiz, will we be allowed to open the slides or the formulas will be given?
Yeah, I will give the formula. The point here is we want to set some sort of a plan so that whatever we are going to do with slides will be with quizzes will be doing with exams. So I'll try to provide the formula, and we are going to build on from quiz to quiz so that you have a set of formulas that you know that it's always with you. So I'm going to provide these.
Doctor,
Yes.
what about the homework, the solution of the homework?
I'm going to post it tomorrow, inshallah.
Okay, thank you.
You're welcome. I'll post it in Blackboard also.
Is the quiz will be multiple choice or we need to submit something?
I have not yet decided that, but anyway, for the quiz, you have to do calculations similar to what you have done in the
Homework.
The multiple choice with only things based on the final answer is something I don't like, because if somebody did like a slight mistake, then the whole thing is going to be out, or the whole thing is going to be considered wrong, and that's what I don't like about the multiple choice. So if I can break the problem into parts and do it as a multiple choice, fine. Otherwise, what we can do is that I can give you like a problems, you can solve it by your hand on a piece of paper, and then after that, scan the piece of paper or photocopy it with your mobile and upload it. Maybe that's another alternative that we can do, inshallah.
Will it be during the class? And also,
Yes.
will it be based on chapter 1?
Yes, chapter 1 during the class, inshallah. It will be something like 15 to 20 minutes quiz.
Thank you, Doctor.
Okay. Any further questions?